Today, I'd like to introduce how to address performance issues in NFV environments, especially focusing on virtual network functions and service chains. Okay, now let's get started. These days, with the advance of system and network virtualizations, network functions that were implemented in hardware are being transformed to the ones in software. So now we can easily deploy various network functions with low cost and complexity. And in terms of service chaining, while we had to make a service chain with multiple middle boxes by wiring them in manual, actually NFV allows network functions to be easily and dynamically chained with the support of SDN. So NFV looks great in terms of flexibility. Then what about the performance of virtual network functions in NFV environments? Unlike hardware-based middle boxes, virtual network functions are highly dependent on host systems, which means that the performance of VNFs would vary according to system specifications. Also, when we talk about NFV, we usually focus on virtual network functions. However, NFV is actually composed of various system and network components, such as hypervisors and software switches. So when we face some performance issues, it is really hard to understand what makes the issues and why they occur, although we may have some guesses based on our experiences. Then let's first talk about how previous works address such performance issues. Previous works mostly focus on some specific performance issues, especially the ones caused by network I/O overheads. So some works introduced high-performance packet I/O engines, and some other works introduced zero-copy packet delivery through their shared memory architecture. And in terms of performance analysis across VNFs, there were some early-stage works. Unfortunately, while they may point out some conspicuous points by comparing the throughput variations between VNFs, their results are insufficient to fully address the reasons of performance issues in NFV environments. So, as far as we know, there was no solutions that fully explain where and why performance issues occur. Then, why is it difficult to address performance issues in an NFV system? A NFV system is generally composed of 4 layers: hardware, hypervisor, virtual switch, and virtual network functions. And as you can see, there are various potential bottleneck points in each layer. And so to fully address the performance issues in NFV environments, actually we need to comprehensively analyze the correlations between these layers. And at this point, you may claim that we already have various profiling tools for each layer. Then why do we still have some difficulty in finding the fundamental reasons of performance issues in NFV environments? The reason that we utilize various tools to understand the performance issues is because we already knew that each tool provides insufficient result. And I also want to point out that even though we have many tools, we still have some difficulty in finding, understanding profiling results, because the amount of data, the amount of the collected data could be too huge to find the correlations between those data. Furthermore, unless we understand how a NFV system works, we may miss some critical factors that cause some performance issues. So it's really important to understand the architectural characteristics of NFV to understand the root causes of performance issues. So here, I'd like to introduce 2 examples that show some unexpected performance degradations. When we deploy new VNFs, we usually focus on various conditions, such as available CPU resources or expected throughputs. However, However, in practice, it is hard to guarantee the performance of VNFs in NFV environments. So the left side graph shows that when we add a new VNF, the overall performance could be unexpectedly dropped, even though unexpected drop and even though the VNF that we deployed is kind of passive VNF that doesn't affect the overall performance. And the right side graph shows that when we change the order of the VNFs, the overall performance could be also dropped. Then, which VNF do you think that causes the performance degradations? So based on simple measurements, it's hard to say what are the major problems in NFV environments. So in this work, we aim to automatically point out where and why performance issues happen. For this, we made two major contributions here. First, we analyzed the architectural characteristics of NFV environments, and then, based on our analysis, we developed a performance analysis system for NFV environments. Now, let me explain each in detail. The behavior of a VNF is much more complicated than what we think. Especially the jobs done in a hypervisor are so important to figure out the reasons of performance issues. Because the hypervisor handles necessary operations such as VM initialization and computation, I/O operation for the actual process of a VNF. So by understanding how a VNF works in a hypervisor, we can figure out how much time a VNF solely consumes for computation, or what kinds of operations are frequently triggered, or how much time a VNF consumes compared to the other VNFs. So in turn, based on these kinds of points, actually we can narrow down the possible reasons of performance issues. And here, we can also think about some other factors that affect the performance of VNFs. In an NFV system, multiple VNFs are connected along a service chain, so it is obvious that a VNF can affect the other VNFs. But VNFs are not the only ones that influence on their performance. Under VNFs, a software switch is actually in charge of the all packet delivery among VNFs. So understanding the operation of a software switch is actually helpful to figure out the performance issues. As a result, with our careful analysis, we defined various performance features for each layer. And when you see these features, you may realize that there are some features are defined in multiple layers, like CPU times. However, those features actually have different meanings. For example, the time at VM side is theoretically the sum of the user and system time of a hypervisor and the CPU time at VNF side. So by measuring the CPU time at VM and VNF size, we can infer the time consumed by a hypervisor. Anyway, by collecting these features from all layers, we can dig into performance issues. After collecting the features, we conduct 3 steps: pre-process and performance anomaly detection and behavior analysis. First, the prerequisite step is to convert the raw data that we collect from all layers to the organized form for performance analysis. Then we figure out which service suffers from performance issues compared to other service chains. Here, the basic idea of this performance anomaly detection is that if there is no performance anomaly, then the outcomes of most service chains might be similar to each other. So by calculating how a service chain influences on the other service chains using a regression analysis technique, actually we can sort out some suspicious service chains that we measured. And as the last step, the goal of the behavior analysis is to specifically point out the reasons of performance issues. To narrow down the range of possible reasons, we categorized the state transitions of VNFs according to the functionalities in a hypervisor, like computation, memory access, I/O operation, or even idle list. Then we evaluate the portion variations of each category in VNFs compared to those in ground truths. In this case, we used single VNF cases as a ground truth values. And in the long run, we summarize the whole result, what features might be suspicious, and how much and why those features are changed. So with all of the information that we produce, actually operators can figure out what is the major reasons of performance issues. To show the effectiveness of our system, we built a NFV system with 7 open source VNFs. And now I'd like to introduce 3 performance issues, and you can also find some other issues in our paper. First, in terms of a single VNF, most monitoring systems focus on VNFs only. However, with our careful analysis, we realize that there are some other processes, such as vhost, that support VNFs outside of them. So as you can see, there are extra CPU usages for VNFs. At this point, while each extra CPU usage might be lower than the original CPU usages, the cumulated extra CPU usages for all VNFs could be higher than a single VNF CPU usages. So those can be critical factors in terms of resource allocations or auto-scaling. And now I'd like to explain the cases that I showed as motivating examples. First one was the case that when we add a new VNF, the overall performance was unexpectedly dropped. And second one was that when we changed the order of VNFs, the overall performance was also unexpectedly dropped. So now let's first talk about on left side first. So when we add a new VNF, in this case TSP dump, the computation time of existing VNFs, Suricata IPS and NOT, got reduced 61% and 28% for each. Then the reason that their computation time decreased is as soon as TSP dump VNF is added, is because TSP dump also start to request I/O operations. As a result, the times for the I/O operations in Suricata IPS and NOT got reduced 55% and 85% for each due to the I/O contentions among these VNFs. Finally, in this case, I/O contentions caused the frequent context switch in VNFs, and resulting in the idle list of VNFs and the overall performance was degraded. And next, I'd like to explain the second case. In this case, the behavior of the first VNF is important to determine the reasons of performance issues. First, when we deploy NES and NOT first, the number of I/O requests significantly increased compared to the case that they come later. And also, when they come first, the available CPU time, available time for NOT is suddenly reduced about 40%. In turn, since the performance of NOT noticeably decreases, the overall performance becomes lower. Behind this result, actually, when we consider the characteristics of VNFs, Suricata IPS originally has lower performance, so it causes internal packet drops. That's what. So the following VNFs relatively handle less number of packets. However, when Suricata IPS comes later, the IPS before Suricata IPS can handle relatively large number of packets. As a result, the performance degradation that wasn't found becomes an issue. Lastly, we evaluate the overall overheads of our system. And as you can see, our system requires a very small amount of CPU resources, which means that it can be even utilized for operational environments. In this work, to address the performance issues in NFV environments, actually we analyzed the architectural characteristics of a NFV system, and then we developed a analysis tool for VNFs and their service chains. With the broad coverage of performance issues, performance features, we collect performance variations across NFV layers and sort out some suspicious performance changes. Finally, we point out most reliable reasons of the given performance issues. And we're currently working on the extension of this for some cloud platforms like OpenStack and some other commercial products. And you can also check out our source code in this GitHub. And thank you for listening. I'm happy to take in some questions.
Let's thank the speaker.